to this afternoon's session after lunch. Our first speaker is Aleksandar, who's from the Mother Teresa University, so expect a very high standard from your talk with a name like that. And Aleksandar is going to talk on fault localization, so take it away.
Thank you very much. So I'll be talking about error invariants for fault localization via abstract interpretation. So fault localization aims to automatically identify the root of an error in a program by localizing it to a relatively small part or slice of a program that contains only relevant statements for the error. Here we consider so-called statement-wise slicing of the error program, where the inferred error invariants, inferred relevant statements can subsequently be changed or repaired in order to generate a correct program. In order to solve this fault localization problem, we are using here error invariants and abstract interpretation. To be more specific, we are using an iterative refinement sequence of backward-forward static analysis in order to compute error invariants, which will explain at every location of the program why a target assertion is violated. The backward analysis computes necessary preconditions at each location for violating the target assertion, and the forward analysis refines the results found by the backward analysis. If there is a precision loss when we analyze if statements, then we use their if guards, to design a BDD abstract domain on which another sequence of more refined backward-forward analysis is performed. And then the inferred error invariants are used to compute this slice of the error program that contains only relevant statements for the error. Let's see our approach through several examples. In this first example, we have a sequence of assignments and then one assertion. The assertion is obviously violated because at the assertion location, epsilon has value x plus 1. So we perform one backward static analysis, which propagates the negation of the assertion fact, x less equal epsilon, from the assertion location backwards. And in this way, at the initial location, we obtain the top element. After that, we perform forward analysis, starting with the top element at the initial location, and we propagate it forward. From the results obtained from the forward and backward analysis, we are computing the error invariants, here shown in red boxes. And they are computed in the way that we are computing the minimal sets of conjuncts from the facts found by the forward analysis that imply the fact found by the backward analysis. For example, at location 3, the conjunct epsilon equals x plus 1 implies the fact x less equal epsilon. So we keep this conjunct in the error invariant. On the other hand, the conjunct z equal x plus 1 does not contribute to this implication, so we drop it from the error invariant. Now, if you look at the error invariants, we can see that we obtain the same error invariants before and after statement at location 3. This means that no matter what statement we have at location 3, the reasons for the error, for the assertion violation stay the same. So this means that the statement at location 3 is irrelevant for the error, so we can drop it from the program slice, where we keep only the statements that are relevant for the assertion violation. So by repairing one of these two statements, we can actually make this program correct. Now we show another example with if statement. In this case, the assertion is violated when the then branch of if statement is executed. In that case, x gets value 0, so the assertion is violated. And this happens when the initial value of input variable is less than 42. So it is obviously that the statement at location 2 is relevant for the error. However, if we perform one iteration of backward-forward, if we perform backward analysis of this program, we start with the negated assertion fact x less equal 0. Then we propagated it backwards. We obtain fact x less equal 0 at the beginning of else branch and top at the beginning of then branch. And this is propagated to top before the if statement, and this top is then propagated to the initial location of the program. So we can see that we are losing precision at the if statement. So if we perform another forward analysis, we will obtain the error invariants shown in red on the right-hand side of the slide. And from these invariants, we can conclude that both statements at location 1 and 2 are not relevant for the assertion violation, which is not correct. And this kind of imprecision we obtain because we have precision loss while analyzing if statement. So in order to obtain better precision, we are doing another iteration of backward-forward analysis, but now we are using BDD abstract domain in which the predicate B is the if guard epsilon less than 0 of the if statement. So if we generate error invariants in this case using this BDD abstract domain, in this case, we obtain more precise error invariants, which will tell us that the statement at location 2 is relevant for the error, while the statement at location 1 is still irrelevant for the error, so we can drop it from the slice for the error program. Now we show one example with while statement. So in this case, we show all error invariants that at each location show the reasons why this assertion is violated. From the error invariants, we can see that the epsilon variable is not relevant for the error for the assertion violation. So actually we can drop from the program slice all definitions of the variable epsilon. So now we can state the contributions of our works. So we define error invariants as abstract representations of the reason why the program might go wrong from some location and violate the given assertion. Then we propose iterative abstract interpretation based algorithm to compute these error invariants. And then we have a prototype tool that is using abstract domains from the apron and BDD apron libraries. And we also have calls to Z3 SMT solver. And finally, we evaluate our approach on a set of C benchmarks. So the language we consider is a simple C-like sequential language that contains statement, arithmetic expressions, and Boolean expressions. we assume that a program is a sequence of statements that end with a single assertion. The concrete semantics is defined over the concrete domain of power sets of memory stores. Then we define invariants, forward semantics, that computes the set of possible stores reachable at any location of the program, starting from some initial set of stores E capital. And we define necessary condition backward analysis that computes the set of all possible stores from which some post-condition F capital might be reached. And this F capital set of memory stores actually contains all memory stores where the assertion, where we have it is actually negation of the assertion fact. It represents all stores where assertion is not correct. Then we define constraint variables of a set of stores S as those variables where whose possible values are constrained in some context. For example, if we have variables x, epsilon, and z, and we have a set of stores where x and epsilon have the same values, then we say that x and epsilon are constrained variables and z is unconstrained variables. Then error invariants at each location are defined as stores from the necessary condition semantics, where we restrict the values of constrained variables such that they are contained in the invariance semantics at the same location. So for example, if we have invariance semantic at location L, which is the store x2, y2, and z3, in that case, and the necessary condition store is this one, is the one above, where x and epsilon have the same values. In that case, the error invariance will be the set of stores where x is 2, epsilon is 2, and z as unconstrained variable can have any integer. And then we show how we can use error invariance to define irrelevant statements in the program. So if we have a program P with some statement inside, and the error invariants in the location before and after the statement S are equal, in that case, this statement S is irrelevant for the error, so we can safely replace this statement with skip statement, and the resulting two programs will have the same error invariance in all locations. So the language is Turing complete, so we cannot compute the concrete semantics. So we want to use abstract semantics in order to compute invariance, necessary condition, and error invariance analysis. So we use the abstract numerical domains D such that they exist this concretization-based abstraction from concrete to abstract domain. Then we define abstract invariance and abstract necessary condition analysis that over-approximate the corresponding concrete ones. And now we show only one iteration of the backward-forward analysis for computing error invariance. So the inputs to this APS analysis are a program, the final error state, and the abstract numerical domain. Then what we do, we first perform backward static analysis to find necessary conditions at all locations, and we also find all predicates that contain if guards, where we have precision loss. Then we find the necessary condition at the initial location. If this condition is bottom, then this means that the program is correct. There is no error, so we can, so we are done. Otherwise, we are performing invariance forward analysis, and then once we find invariance at all location, we are finding a minimal support set such that the facts from the first parameter imply the facts from the second parameter. And this minimal support set is found by via calls to Z3 SMT solver to compute unsatisfiability cores. And this procedure returns at output error invariance at all locations, the refined error state at the assertion location, and the predicate set P. And then our iterative abstract analysis for computing error invariance actually is a while loop where in each iteration we call this ABS analysis using given final error state and abstract domain. If the refined error state is bottom, in that case the program is correct, so the return program slice will be only skip because there are no relevant statements for the error. Otherwise, if it's not bottom, in that case we refine the abstract domain on which we will perform the next backward forward analysis. So now we use BDD abstract domain, where as predicates we will use the if guards generated using backward analysis. And this loop will terminate when the predicates and refined final error state stay the same over 2 iterations. At that point, we have generated error invariant, the most precise error invariance in all locations. And after that, we use this slice procedure to generate the slice of all relevant statements for the error. And this slice procedure basically checks whether the error invariants at the location before and after a given statement are the same. If they are same, then replaces the statement with skip because the statement is not relevant for the error, otherwise it keeps the statement. So we have implemented this, this procedure in OCaml. We are using the numerical abstract domains from the apron library. And for the experiments, we use polyhedra domain. Also we use BDD abstract domains from the BDD apron library. And we have calls also to Z3 SMT solver in order to compute minimal support sets. So we are comparing our procedure with the fault localization tool BackAssist, which uses the CBMC bounded model checker to generate an error trace where the assertion is violated, and then this approach analyzes the corresponding trace formula using MaxSat solver. The third approach that we are using is we use only single backward analysis to compute this error invariance. So we are using some of the benchmarks that are standard in this literature for fault localizations, like TCAS suite or some programs for CV comp suite. And for each of these three approaches, we measure the running time, the size of the resulting slice, and the precision compared to the results that would be computed if we use concrete semantics. So we can see that our approach on these benchmarks achieves better results performance-wise, precision-wise, sorry. If you look at the performances, of course, the approach that uses single backward analysis is faster, because in our approach we might have several iterations that are done in order to generate more precise results. And the performance results between our approach and back assist are comparable, except that back assist depends on the degree of unrolling the loops. So at the points where we have some while loops, its performances might degrade, because this approach might need more unrollments of the loops. So to conclude, in this work we have proposed error invariants that provide semantic arguments why certain statements are relevant or irrelevant for some error. So in a way we have provided statement-wise semantic slicing of error programs. Then we have presented an algorithm that infers error invariants, and we use them for fault localization of error programs, and we have evaluated our approach on a set of C benchmarks. Thank you.
Okay, questions from the floor?
So thank you for the talk. This is going to be a super quick question on your slide where you said the experimental results. You mentioned the performance as a percentage. I probably just missed it. Could you explain what this percentage there is?
So the percentage is we are comparing the precision of the results with respect to the results that we would obtain if we have concrete analysis.
And precision?
If we use precision 100%, it means that we have precisely identified relevant statements for the error.
So in terms of the identified
relevance,
statements.
yeah.
Okay, yep, thank you.
Okay, next question. Okay, well, if there's no question, I will ask a question. From the way you explained bug assist, and I'm completely unfamiliar with bug assist, it seemed to be doing something which is a bit like lazy abstraction and interpolation.
Bug assist?
Yeah, bug assist. So I wondered why you sort of didn't compare to like a lazy abstraction method, because the idea of computing an interpolant up to the error.
Yeah, they are using interpolants.
They are?
Yeah.
Oh, okay, fine. Thanks for clarifying that. I had no idea.
Because they create this trace formula using CBMC model checker.
Right, I see.
And then in the trace formula, they are with this max sat solver, they are kind of finding interpolants at each location.
Oh, I see. So the max is just a way of picking out these sort of relevant constraints for unsatisfiability, is it? Okay, right. Thanks for clarifying that. Any more questions? Oh, yes.
How much of the performance is, or how much of the running time is contributed by the solver calls? Is that like the thing that's bounding the performance of this tool, or is it other parts of it?
So I haven't measured here, I mean, but I don't think so that the calls to this Z3 solver takes a lot of time. I think more of the time performance is degrade when we use this BDD abstract domain, and then the whole forward and backward analysis are performed on this BDD abstract domain, and those cases have degrade of the running times.
Perhaps I can have a related question. Can you comment on how many nodes you have in your BDD domain? Because when I've done BDD work, I've noticed that the running time is very, very sensitive to the number of nodes.
Yes.
It can be fine, then you push it a bit and it all goes bad.
So, I mean, it's obviously that here we have tested with relatively small benchmarks. So this TKS example has a lot of ifs. So that's why at that point we obtain some bigger number here.
Right, okay.
Because in that case, maybe we can have maybe 10 if guards where we have imprecision. So at those points, we can see that the performance is degrade significantly.
Okay. Any more questions from the floor? Going, gone. Okay, let's thank our speaker again.